All right, guys, good morning. So welcome to almost the end of this lecture series. We have a few more lectures to go, but now we'll start with the promised invited speakers, and I'm very happy to have today Amar from the 6th floor where RISE 6 is, Swedish Institute of Computer Science, and he's a researcher in the AI lab there, working with natural language processing. And he's also in the last year of his PhD. So you will sort of have access to the state-of-the-art people who are pushing the boundaries in the area, and will be able to hear, the latest news. So maybe it's more fundamentals, but but anyway, from the person who pushes the boundaries. We will also have one more invited speaker on privacy-preserving data mining, and I think that will happen not next lecture, but lecture after. And I hope I will finish my own material during the next lecture, because I was a bit also overflow. I thought we will finishing on Wednesday, but we'll probably have one more lecture. So I will then simply will not bother more. I'll give the floor to Amaro, and he will teach everything about NLP.
Everything, yeah. Okay, yeah. So I'm just gonna go to the outline here. So what I'm gonna talk about today is, a brief overview of what and why of natural language processing. What is it? Why are we doing it? I'm also going to talk about the particular subfield of natural language processing that I am working on is distributional semantics, or like natural language understanding, and ways of quantifying the meaning of, in particular, text. And the history of that, if you go back, that's the field of distributional semantics and within linguistics. So I'm going to talk about the history of that and how kind of follow the thread up until today, where we have contemporary language modeling. I don't know how up to it's kind of hard when you're in the field. You know what's happening and you think that everyone knows what you do, but obviously that's not the case. But so a quick show of hands, how many of you have heard about or knows about Word2Vec, for example? A few, yeah. And Elmo? Bert? No. Okay. Yeah. Yeah. Okay. Yeah. So not that many. That's good to know. I will, but I'm going to talk about that later, and then kind of progress into the uses of natural language processing and what you need to think about and what the possibilities are, essentially. So yeah. In short, natural language processing is the processing, modeling, exploitation of natural language data. And natural language data, the most obvious example is text, because there's an abundance of text. But it's not, it's not necessarily only text on the internet, like tweets or Facebook comments. It's also speech recognition, or text-to-speech is a problem within natural language processing, speech-to-text, and vice versa. Another famous example is machine translation. A less famous example might be word segmentation. So when you treat natural language text, how do you actually segment a word? What is a word? Depends on what you're trying to do. If you're an editor, if you're making a text editor and you want your user to double click so they select the whole word, then you actually need this. And if you're doing distributional semantic models, you also need this. But it's kind of it's not as flashy as the other as a lot of the other parts of natural language processing. And we also have things like optical character recognition, OCR. So a lot a lot of the text we have today is generated on the internet, but we do have a lot of historic text, like books, reports. I mean, if you're working with like government agencies, then they have these little, like everything is paper, and then they took a photo of a paper and they made the photo into a PDF, and then you want to analyze the text that they have, and it's a complete mess, because yeah, you need to go then you really need to be able to have like good OCR techniques to make that PDF of a photo of a text manageable, essentially. And what I'm most interested in, and also what I think is that the general public is the most interested in, I don't know to which extent that is true, is natural language understanding. Like, how do we get computers, or how can we automatically create semantic representations of language? And in particular, how can we create representations of semantic representations of text? There are a lot of applications of that. Like if we dig deeper within textual understanding, you have things like sentiment analysis. People writing hotel reviews on I don't know, TripAdvisor, or product reviews on Amazon. You take those reviews, you try to build a classifier, and then you see like, okay, yeah, now we're not limited to our analysis of these products within this, like within Amazon reviews or something. We can look at when people talk about these products online, try to transfer the models that we have trained on the reviews, and see like, okay, yeah, people are positively or negatively inclined towards our products. And you can also document classification, like in the previous example with like a government agency emails or something. Someone emails the tax agency saying, I have a problem with my declaration, I have a problem with my taxes, and then maybe you have this ontology of like, okay, yeah, it's this kind of problem or that kind of problem. So you want to put these this big bag of texts in different bins. It's also it's a simplifying application. You also have information retrieval. So I mean, if you do a free text search, for example, if you Google boat, you won't only get examples of web pages that contain the word boat, or because the word boat appears in a lot of different. I mean, there are many synonymous terms like ship or barge or schooner, or yeah. So you want to have a not only the actual surface form of the text that you supply, or like the text that you're trying to get at, but you want to get at the semantics, like the deeper meaning of that text. And more recently we've been seeing big improvements in like the field of question answering. So you can train a model on a bunch of text or Wikipedia or something, and you ask like, oh, what's the medium temperature in Stockholm in July? And you can you will get an answer to that. Or more commonly, you would have a short text, and then you can like Emily went to the store to buy some bread. She bought 2 eggs and a baguette, and then met John or something. And then you say, and then you can ask, then you can query the model like, okay, so where are the eggs now? Or who has the baguette? Maybe John took it. Or like, where is Emily now? So yeah, there are. What I'm trying to get at here is that there are a lot of applications of textual understanding, and it's not at all a trivial. It's not trivial problems, but it's very useful. They're very useful if we can solve them adequately, right? Another example is, like summarization. You have a bunch of different news articles online, and you want to get a quick summarization. What is going on here? Or I don't want to read this long article, so I trust this program to summarize it for me. And And one of the upsides of using text as a data source is that the language itself is a very rich and informative data source. We use language quite effectively all the time to communicate, and it's not that much. It's not that much raw data. Like if I send someone a message, it's a couple of bytes, but it's incredibly informative. It's also abundant. There is, just text is readily available essentially anywhere, and there are a bunch of open data sets. If you have the money, you can buy data from data providers or like social media platforms or whatever. These are like figures from 2018. So 2018 there was 500,000 tweets per minute, 500,000 Facebook comments per minute, 300,000 Facebook status updates, 16 million text messages. These are all per minute globally. 156 million emails. I'm not sure about this figure. It seems weird to me that there's a lot more emails than text messages, but I guess there's also a lot of automated email messaging systems. And 100 million spam emails. So we both have a reason to classify text as spam and not spam, and also a lot of available data to enable that product. So, if you have a good, adequately trained language model that, in some sense of the word, understands text, you can build on top of that relatively cheap applications leveraging language understanding. And so in I think it was 2016, OpenAI published this sentiment neuron article on their blog. This is not peer-reviewed research, which is a very important thing to point out. But what they essentially found is they had a deep recurrent neural network trained on a bunch of general text. They didn't not necessarily train on sentiment. So it's not a supervised model. It's just trained on understanding language, predicting the next character in a sequence. And they noticed that they could find one particular neuron in this model that correlated to a very great extent with sentiment in the text. And this is the activation of that neuron at that step in the process of analyzing this text. So, this is, as I said, this is not peer-reviewed research, but the general gist is there. Language is a very informative data source. If I say something that's with negative sentiment, you understand that as a person, right? And you can probably understand what I'm going to say, or the gist of what I'm going to say. I'm not going to say something positive all of a sudden. I'm going to, so it's, that's the big upside of using text. You don't really necessarily need to have all this labeled data. immediately at least. So another topic that is being employed like in the social sciences is topic models. So you want to understand like what, if we have a bunch of documents, a bunch of texts, maybe like various news sources, news articles, we want to understand the distribution of topics that are floating about in this space. So you could also look at like how you can try to model like what's the generative process creating all these documents that we're observing, and then you can kind of use that in this. It's used very much in the social sciences, in like political science and media science, in for some kind of quantitative analysis on large text. So like, oh, okay, yeah, we see that this is an example of, I think, Sherlock Holmes. So the documents here are like various Sherlock Holmes novels, and then then you can see that in this, I don't really know. It's kind of hard to analyze, and this is a big problem with topic models in general. But yeah. So with does anyone have any questions? By the way, you're just free to ask if you have any. All right, no, yeah. And so now I am going to talk about the history of distributional semantics. I'm just introducing a term here that I haven't used before, but stay with me. I mean, it's kind of the theoretical framework or idea that underlies most of these models. And it's not a very complicated or like groundbreaking statement. It's just that. It wasn't Firth who, Firth is not the father of distributional semantics. He was the one who coined the phrase that is now an all but mandatory quote when you do research in distributional semantics or natural language processing. So the idea is that you should know a word by the company it keeps. What this means is that I mean, yeah, in most cases, the meaning of a word is its use in language. Or equivalently, words which are similar in meaning occur in similar contexts. Or even more, yeah, two words are semantically similar to the extent that their contextual representations are similar. So what we're kind of getting at here is that by looking at how words are used in language, we can create very good semantic.
Just try to.
Oh, okay.
Things more visible.
We have an ability to create very good semantic representations. I mean, the extent to which we know how we ourselves learn language is, I'm not at all an expert, but it seems fairly natural that we learn language by observing and testing how language is used. It's not a very bold assumption. So I mean, all of these researchers essentially, like they can trace their theoretical history or like their ideas to Selig Harris, this guy, and his work in distributional structure. And he was a linguist, sometimes said to be the father of computational linguistics. And while he did not explicitly formulate the distributional hypothesis, which is what I've just showed you, that this general sentiment that, yeah, the The meaning of a word is its use in language, or a word is known by the company it keeps. All of these are distributional hypotheses. But he stated that language can be understood in terms of the occurrence of parts relative to other parts, and that the distribution of an element is the sum of all its environments. And this is kind of the same statement. What he means by an element here can be a morpheme or a term, a word. And what he means by by distribution, he means, and yeah, by environment, he means like the context it appears in. And exactly how you interpret that, I mean, like sum could be, oh yeah, like a multi-set sum. If you just look at like, okay, all the neighboring words of this word, or the document, or there are a lot of ways to understand this, and there are a lot of different understandings of it, which we will see. So when you kind of put these ideas into practice, and this was done quite early. This was done even like in the 70s in the field of information retrieval. So what they did at that time was that, yeah, if you have a bunch of documents containing words, you characterize each word as the documents it occurs in, and each document as all the words that it contains. So you would end up with this like term document matrix. I mean, here we have I don't know, some document which we call document 1 contains good, bad, and blue. For some reason, I mean, you would have a lot more words here and a lot more documents, but that's the general idea. And so this was introduced in 1975 by Salton et al. Called I think it's called a vector space model for automatic indexing. I mean, this works fairly well. Like if you want to find documents that are similar, you find them by like their term overlap, right? Like maybe we have other documents talking about awesome green stuff. Then we will see that they have a large term overlap with document 2. And also, this does contain some information about like the terms itself, right? So words that are commonly used in the same documents as good, we could find them by looking at their document overlap. And the problem with this is that, I mean, synonymous or similar words, you don't really account for it, right? Because every word is just discrete, singular thing. Doesn't have really a meaning besides its surface form. And I mean, apart from that, if you do this, if you have millions of documents and thousands and millions of terms, you end up with this like wild, unwieldy, sparse matrix representation that is not really that amenable to analysis. So what do you do? And in the 80s, they came up with the fact that you can factorize this term document matrix. Right? You can make you can find a matrix factorization of this matrix with like a low rank factorization. So here we have like what was previously document 1 and a bunch of terms is now document 1 and what they call a latent factor. So the first latent factor and the second latent factor. And now all these documents are represented in terms of their latent factors, and all of the terms, all of the terms are also represented in terms of their latent factors. So now, since you have this low rank representation, it's much easier to perform analysis. I mean, just computationally, like if you have a 100-dimensional representation that's much nicer, like dense representation that's much nicer to work with than a million-dimensional sparse representation. And this does, to some extent, like tackle the problem of synonymy and word similarity, because if you because if you do this like low-rank factorization, to some extent, it becomes beneficial for the model to give quite similar latent representations to semantically similar words. So another approach to this term document modeling is latent Dirichlet allocation, which is this is the absolutely most common topic. Like this is the basis for topic models in general. And there you kind of assume a generative process. So instead of doing this tabulation, you count all the documents and all the terms in they occur in. You try to fit this probabilistic model based on this generative process. We assume that like a document is about some mix of topics, and usually like a spiky mix of topics. And it has some length, sampled from a Poisson distribution. That one is not super important. And then we assume that each topic is a distribution of words. So if I'm talking about baking, I have like my vocabulary will follow a particular distribution, whereas if I'm talking about soccer, I'm like the distribution of words I'm going to use are wildly different. So that's a general idea, and it's this that creates this little picture of Sherlock Holmes word usage topics that you saw before. And another venue is the term models. So if you don't care about the documents, if you're just interested in like, okay, what do words mean, or how do we use them, what we can do is we can model terms directly by the terms they occur with. And this is, I mean, if you imagine that we are talking about tweets, for example, I mean, topic models are infamously bad at representing tweets. But one part of that is that like a tweet as a document is quite strange. Probably doesn't talk about that many topics. Probably just one. Might not even talk about a topic at all. And it might just be like. Yeah. So what you can do instead is like you can do this: model terms directly by the other terms that are being used with it. This is by now the more common and popular framework to work with it. So going back to these like original tabulating methods, you would end up with this term matrix. So cash and bank occur within like a window of so and so many words 300 times. Cash and interest also occurs. Sport and bank does not occur that many times together, and so on. And like the factorized term document models, you can also apply factorization methods to the term matrix, which once again gives you much better or much simpler dense representations. So this was done as early This was done in 92 by Ritze in his Dimensions of Meaning paper. And there you have some examples of semantic neighborhoods that you get out of that. So absolutely is, according to the model Ritze published in 92, similar to a word like absurd or whatsoever or totally or exactly or nothing and thus. These are obviously not state of the art. This is this is some more than 20 years ago. But I mean, you do. I mean, you can kind of get at the fact that you can capture to some extent, the semantics of words using these very, very simple distributional distributional methods. But I mean, a problem with this approach, right, is that it's not necessarily immediate what we're actually capturing. What do we mean by a semantic neighborhood if doghouse is similar to crawling?
Sorry, just to understand, so that means absolutely was similar to absurd, because when you had term and term matrix and you mapped to some low-dimensional space, they were similar in that low-dimensional space by the distance.
Yes. Yes, that's exactly what I mean. And well, in particular, it's normalized. So you map them down to this low-dimensional space, and you normalize all the vectors, so that they're on like a hypersphere to account for difference in frequency.
And you say it wouldn't perform as good, whatever the performance mean, as if you had the same representation from term document.
It's different, right? Or what?
But no, I could have, asked what's the distance from absolutely and whatsoever in this your previous example.
Yes.
They were like, say, several latent dimensions that were there, and then you had some distance. And you could have made the same or similar table, and now you say that you have this term to term, and it's somehow better.
Yes, I will. I'm just going to show you the next slide.
I just want to understand why. I see that it's a different, but I'm not sure I understand why suddenly this is somehow more.
It depends, that's what I'm getting at. Like, what do we actually capture with these models? And these are quite old terms in linguistics. So you have paradigmatic relations and you have syntagmatic relations. Paradigmatic relations are like words that are interchangeable in a context. So to some extent, dog and cat are paradigmatically related words. Good and bad are also like interchangeable. They don't necessarily mean the same thing. I mean, good and bad are antonyms, right? But antonyms have this interesting property that they are usually very similar to synonyms in the way we use them, right? And then you have syntagmatic relations, which is words that occur together. So like dog and bone, or good and movie. And so this is actually the difference between the representations you get from a term document model and a term model. In a term document model, you largely get syntagmatic relations. Because, like all the words that occur together obviously occurred in the same document, but you don't really have much information about their interchangeability, right? If you look in a small window of words and you say that, okay, dog comes after A, And I mean, immediately you have like injected a lot more grammar and syntax and like interchangeability properties in your model. So that is the main difference. And if we go back to this, is it up? Yeah. If you go back to these neighborhoods, I would argue that it's quite obviously a mix of paradigmatic and syntagmatic relations that we're seeing in these neighborhoods, right? So I mean, absolutely and nothing are probably a syntagmatic relation, whereas absolutely and totally are a paradigmatic relation. And in a term documents model, you would have a lot more of the syntagmatic relations. So yeah, so what we capture kind of depends both on the model that we're using and our mode of query. Like even in term models, you can imagine that you can. I mean, yeah, you can get at the syntagmatic relations by. I mean, if you look at the actual matrix representations, the actual count representations, then it's quite easy. You just look at, okay, which has the highest count for this word, like which word co-occurs the most with this. With dog, then you will get probably A or the. And then, I mean, I haven't really talked that much about the specifics of how these models work more in detail, but you also have a lot of like weighting schemes to weigh down the importance of uninteresting words like the and A. But anyway, so this is kind of the history and the background of distributional semantic models. And in like early 2010, not that long ago, there was kind of a big shift. So instead of having these big tabulations over terms occurring with other terms and terms occurring with other documents, people started looking at predictive models. So this is the title of a paper published in 2014, which compared a lot of different language models at the time. They're all outdated now, but I mean, but the general trend that they identified was that, I mean, at the time there was a lot of hype regarding the predictive neural network models. Some of them deep, some of them shallow. I mean, Wörterweg was published 2 years earlier, and that was quite a. I mean, that was a big change in the way people thought about language modeling, and it also like. Yeah, what they found essentially was that count-based models are much worse at practically everything compared to prediction-based models. And yeah, and what you do in a predicting, like so this is an example of essentially like a term predictive model. So you have you have this like occurrence of a word mat, and the surrounding context is the previous words. The cat sits on the and so now what you're trying to do is you're trying to have you construct some model that tries to predict which word comes after, or like which word comes after the observed words, essentially. I don't know, should we take a break there?
No, it's 5 to 11, so we can take How much material do you have?
I don't know, 5? No, but I have like 2 sections, or like one. What I have is the kind of like what has happened since Word to Vec, and what has happened since like the current predictive models and how they are used. And I mean, I'm not going into detail on how the actual models are defined. Mm-hmm. It's a very high level. Very high level talk, but and then I have like the uses of.
15 minutes break, is it enough, or
yeah.
Or you take 10 minutes?
No, 15 minutes is fine.
Okay, so let's take 15 minutes break.